Let us talk about the potential difference due to a line charge. Okay, so potential difference due to line charge. We may consider infinitely long line charge. So how to find out potential difference due to an infinitely long line charge? Okay, so let's suppose this is our charged wire. This is infinitely long charged wire, and we want to find out the potential due to this wire. Okay, we want to find out the potential due to this wire at some point. Okay, so what do we do? So see, now we know the formula for electric field, and we found the relation between the electric field and electric potential last time, right? So the formula for electric field due to this charged wire, infinitely long charged wire, is given by E is equal to lambda divided by 4 pi, sorry, it is 2 pi epsilon naught r, right? Electric field due to a charged wire is lambda divided by 2 pi epsilon naught r. Okay, and what is its direction? So if we consider any point, let's say we consider this point, let's call it point A, then the electric field due to this wire at point A is along this perpendicular line. Okay, so it is along the perpendicular line. So we can say it is along n cap. Okay, or if this distance is r, then we can say that, okay, if we draw a perpendicular from point A to the point O, okay, then it is along this perpendicular. Okay, so we can say it is along r cap. But what is r? It's the perpendicular distance of this point from the wire. So now I want to find out the potential. So what should I do? I know the relation between the electric field and electric potential. So we know that E is equal to minus of dV by dr. Okay, so in this case, only this direction matters, right? Only this direction matters. So we can say the change in potential is equal to minus of E multiplied by dr, right? So, okay, using this we'll get change in potential, small change in potential. Then suppose we take 2 points. This is point A, this is point B. Okay, the potential difference between these 2 points will be what? It will be integral of this dV from point A to B. Okay, or actually potential at A will be more than potential at B. So I can say it is integral of dV from B to A. So suppose lower limit is B, upper limit is A. So what we get? It's equal to minus of integral of E, which is lambda divided by 2 pi epsilon naught r dr from r of point B to r at point A. Okay, right? And then, so lambda is constant, 2 pi epsilon naught is constant. We can take it all outside. So what do we get? So it is VA minus VB. Okay, potential difference between these 2 points. It's equal to what? Lambda divided by 2 pi epsilon naught. We can take out, and its integral, okay, it is minus of integral of RB to RA of 1 upon R dr. And what is this integral? It is log of R, log of R, right? Natural log of R. Okay, so it is equal to, we can say, minus lambda upon 2 pi epsilon naught, okay, log of R, and the limits are, lower limit is B, so it is RB, upper limit is Ra. Okay, this is Va minus Vb. And then we can substitute the lower and upper limits. Okay, we can substitute lower and upper limits. So what we get? We get minus lambda divided by 2 pi epsilon naught, and it is log of Ra minus log of Rb. Okay, but notice that point B is at greater distance, right? Okay, so Rb is greater than Ra. That means since Rb is greater than Ra, log of Rb, log of bigger number will be bigger, right? So what we can do, we can take this minus sign inside. Okay, we can take this minus sign inside. So we get lambda divided by 2 pi epsilon naught. Okay, and then I can write log of Rb minus log of Ra. Or you can write this as, okay, this is log of B upon, log of Rb upon Ra. Okay, this is lambda divided by 2 pi epsilon naught log of Rb upon Ra. Okay, this is Va minus Vb. So this will be the potential difference. This is potential difference due to infinitely long straight wire. Okay, so see, now potential at A will be greater than potential at B, and this is as expected because point A is closer to the wire compared to that of the point B. Okay, so yeah, is this thing clear? We'll talk about capacitance. Now suppose I have a negatively charged rod. I bring it close to this metal hollow sphere. So what will happen? So the electrons from this metal hollow metal sphere, they will get repelled. Okay, and some positive charge will appear here. Some positive charge will appear on this side, and negative charge will appear on the other side. And then what you do is you take some wire. Okay, you connect it over here, and you remove that excessive, not excessive, that negative charge. Okay, so what will remain? And then you move this rod also. Okay, you move this rod away. So what will remain? There will be a positive charge. Okay, there will be a positive charge on this conductor. Okay, so you remove all this. So you have induced a positive charge on this conductor, right? So now this positive charge will be stored on the conductor. Okay, this positive charge is stored on this conductor, right? And it will produce some potential. It will produce some potential. So this capacity of a conductor to store an electric charge, it is known as its capacitance. Okay, so what is capacitance? It's capacity of a conductor to store an electric charge. So actually what we have done is basically we have stored some energy in the form of an electric charge on this conductor. I'm sorry. So see, the capacity of the conductor to store the electric charge is known as capacitance. Okay, so now how do we measure that capacitance? So to measure capacitance, we take ratio of charge to the potential difference. Okay, so here we have single conductor, so we measure its potential with respect to infinity. Okay, so what is potential produced by a hollow metallic sphere? Potential produced by hollow metallic sphere is what? 1 upon 4 pi epsilon naught multiplied by q upon r. So if we substitute this in this formula, we get capacity or capacitance of a hollow sphere. And see, if you substitute it here, q and q will get cancelled. This 4 pi epsilon naught r will go in numerator. So we get 4 pi epsilon naught r. This is the formula. Capacitance of hollow metal sphere. Okay. And the unit of this capacitance is coulomb per volt. It is coulomb per volt, right? Unit of charge is coulomb, unit of potential difference is volt, and this is known as farad. Okay, this is known as farad. So now, see, 1 farad is very big capacitance. Okay, 1 farad is very, very big capacitance, right? So, for an example, how big of a sphere will need to store charge of 1 coulomb at a potential difference of 1 volt? So, to find out that, we know 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught is 9 multiplied by 10 raised to 9. Okay. So let's consider this question. Find the radius of a metal sphere having capacitance of 1 farad. Okay. So we know now C is equal to what? 4 pi epsilon naught R, and capacitance is 1 farad. Okay, so this is 1 farad is equal to 4 pi epsilon naught multiplied by R. Okay, and we also know that 1 upon 4 pi epsilon naught is equal to what? 9 multiplied by 10 raised to 9. So what would be 4 pi epsilon naught? It is 1 upon 9 multiplied by 10 raised to 9. Right, so this is R divided by 9 into 10 raised to 9. Okay, so capacitance is 1 farad. Now move that 9 multiplied by 10 raised to 9 on the other side. Okay, R is equal to, we get 9 multiplied by 10 raised to 9 meters. Okay, so how much is this? We can roughly say it is 10 raised to 10. Right, and how much is radius of Earth? Radius of Earth, 6,400 kilometers, or we can say it is nearly equal to 6 multiplied by 10 raised to 6 meters. Okay, so this is roughly, not roughly, yeah, roughly 1,500 times more. Okay, it is 1,500 times more compared to the radius of Earth. Maybe it is as big as radius of Sun. Is it so? Okay, I don't remember what is radius of Sun, but this is very, very, very big number, right? Very, very large distance. Okay, so we cannot construct a capacitor whose capacity is 1 farad. It is very, very huge number. Okay, so in practice, what capacitors are used are picofarad. Okay, in practice, we use capacitors having capacity of picofarad or nanofarad or microfarad, and max to max there will be something of capacity millifarad. Okay, so pico is 10 raised to minus 12, nano is 10 raised to minus 9, then micro is 10 raised to minus 6, milli is 10 raised to minus 3. This we know, right? So is this thing clear? So let's talk about very general capacitor, which is parallel plate capacitor. Let's see the parallel plate capacitor. So what is parallel plate capacitor? So we have two plates kept in parallel with each other like that. This is one plate and there is another plate. They are kept like this, very close to each other. So now see, now what will happen if you keep two plates like this and there is some positive charge. Some positive charge is deposited on the first plate. Let's call it plus Q. Okay, so charge is plus Q. So if you have plus Q charge on one plate, then what will happen? Minus Q charge will get induced on this side of the other plate, and on the other side you will have plus Q charge. Okay, so now what you will do is you will remove that plus Q charge on the other plate by connecting a wire. Okay, by connecting a wire, you connect it to down and you remove that plus Q charge, okay, from the other plate. So the other plate will have minus Q charge on it. Okay, it has minus Q charge, right? This one has a positive charge, and this plate has a negative charge. Okay, so actually, how much charge we have stored? We have stored charge equal to Q. Okay, the other charge is induced, right? Other charge is induced. So now there will be some potential difference between these two plates. Okay, so we'll find out the capacitance as the charge, which is Q, divided by this potential difference between the two plates. Okay, so in earlier case, when we had only one conductor, this one conductor, the reference point was infinity. But in this case, our reference point is potential of this plate, the negative plate, right? So see, now how do we find potential? So let's suppose this is my first plate. Suppose this is my first plate. This is my second plate. So there is some positive charge here. How much is the charge? It is plus Q. There is some negative charge. It's minus Q on the other plate. So now let's consider these 3 points. Okay, let's call them A, B, C. Let's find out the electric field due to these two plates at these 3 points. Okay, so see, now electric field due to this plate, positive plate, will be sigma upon epsilon naught. We have studied this in last chapter. Okay, so we know electric field due to a charged conducting plate, electric field due to a charged conducting plate is given by, it's given by what? E equals to sigma divided by epsilon naught. So electric field due to positive plate will be sigma positive, we can say, divided by epsilon naught, and electric field due to negative plate will be sigma negative divided by epsilon naught. Okay, sorry. So both plates are identical. Suppose, sorry, suppose both these plates are identical. So the electric field due to positive plate will be sigma upon epsilon naught, and electric field due to negative plate will be minus sigma divided by epsilon naught, we can say. And magnitude of EP and EN, it will be equal. All right, let's not do this. Okay, so okay, let's suppose both plates are identical. Both plates are identical, right? And both plates have equal amount of charge also. But charge on this plate is positive, charge on this plate is negative. So now if we consider this point, so at this point the electric field due to positive plate will be directed like this. This is EP. Electric field due to negative plate will be directed like this. This is E due to the negative plate. Okay, because if you keep a positive charge over here, it will get repelled by the positive plate. and it will get attracted by the negative plate. So electric field due to the positive plate is outwards, electric field due to negative plate it is inwards. Okay, so now since the electric field due to both of them have equal magnitude, so I can say because surface charge density is equal, EP bar, magnitude of EP bar and magnitude of En bar, it is equal. Okay, which is sigma divided by epsilon naught. So what will happen at this point? The net electric field will be equal to 0. Got it? Yes, no? Okay. And similarly, we can reason for this point also. At this point, also the electric field due to the positive plate will be directed like this. Electric field due to negative plate will be directed like this. Okay. So net electric field at this point will also be equal to 0, right? But at point B, the electric field due to positive plate, it is directed like this. Electric field due to negative plate is directed like this. Okay. Electric field, if you keep positive charge over here, it gets repelled by this positive plate. So electric field is outwards. Okay. It's in this direction. We can say positive x direction. And the electric field due to negative plate will be towards the negative plate. And again, the direction is same. It is again the positive x direction. So the net electric field at point B, which is a point inside the two plates, it is sum of these two electric fields. Okay. So we can say net electric field at point A and C, that is outside the capacitor. Okay. Outside of two plates is equal to 0. Okay. It is equal to 0. Right. And net electric field inside the capacitor, you can say point B, E is equal to what? EP plus En. Now I am considering just magnitude. It is sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught. Oh, here I did a mistake, right? It is sigma divided by 2 epsilon naught, not epsilon naught. Okay. So electric field due to plate is sigma upon 2 epsilon naught, right? And if we add these two, then what do we get? We get half plus half, sigma upon epsilon naught, that is 1 sigma upon epsilon naught. I'm sorry. So this is the electric field due to two parallel plates, and it is electric field at a point which is inside those two parallel plates. Now, what will be potential difference between these two plates? What will be the potential difference between these two plates? So charge on first one is plus Q, charge on second one is minus Q. Okay. And let's suppose distance between them is D. So now we found the electric field at a point which is inside these two plates, and we don't know anything else about that point. Okay. So if these are infinite plates, then we can say I'm sorry, we can say electric field at all the points inside will be equal. Okay, electric field is same, and we know electric field is equal to what? Minus of dV by dr. So in this case, we can say since electric field is constant inside at all the points, So we can say it is minus of V of this positive plate, or let's call it potential difference, delta V by dr. Okay, and what is dr? Dr is this distance. Okay, let's call it V1 minus V2. Okay, the potential difference. And therefore we can say, so V1 minus of V1 minus V2 is equal to E times D, and that is, you can say V2 minus V1. Okay, V2 minus V1 is E times D, right? So what is V1 and V2? So see, electric field will be directed like this. Electric field is directed like this. So now you take uh, this one as 2 and this one as 1 if you want positive electric field. Okay, so electric field is directed like this. Potential on this plate will be higher compared to potential on this plate. So what is V2 minus V1? It is the potential of positive plate minus potential of negative plate. Okay, and let's call that potential difference as V. Okay, so suppose V2 minus V1 is equal to V. So V is just equal to E times D, or you can say it is equal to, what is E? So E is sigma upon epsilon naught, okay, times D, right? And what is sigma? Sigma is charge upon area. Sigma is charge upon area of the plate. So we can say V is equal to charge upon area times epsilon naught multiplied by D. Okay, and now we did all this to find out what? We did all this to find out the capacitance, and therefore I can say the capacitance of a parallel plate capacitor, C, which is equal to Q divided by V. So you move this V on the other side and this A epsilon naught on this side, D on this side. This will go to the numerator, this will go to the denominator. So what do we get? We get epsilon naught A divided by D. Okay, capacitance of a parallel plate capacitor is epsilon naught A divided by D. Got it? Yes, no? So this is capacitance of air filled capacitor. We didn't consider any medium inside these two plates. So suppose there is some medium. Suppose there is some dielectric. Okay, dielectric meaning some insulator is there. So it will have some dielectric constant K. Okay, so capacitance in that case will be K times epsilon naught A divided by D. Okay, capacitance in that case will be, so for a dielectric, for parallel plate capacitor, filled with dielectric, C is equal to epsilon naught Ka divided by D. Okay, this will be the formula. We'll talk about this in detail, but okay, we have to memorize the formula also. So I'm just mentioning the formula. Okay, it is epsilon naught Ka divided by D. Right. So let us find out next capacitance of concentric hollow spheres. Okay, two concentric hollow spheres. See, suppose there is some charge on this inner sphere. Okay, the charge is suppose plus q, and there is some charge on the outer sphere. Charge on the outer sphere, suppose minus q. Okay, it is suppose minus q. So I want to find out the capacitance of this kind of arrangement. We have two concentric spheres, right? And the outer sphere is suppose connected to the ground. Okay, that means we have taken out the positive charge out of the outer sphere. Okay, so now see what will be the potential difference in this case. So let's suppose the radius of inner sphere. Let's suppose radius of the inner sphere is RA. The radius of outer sphere is RB. It is RB. Okay. So we know potential due to a charged sphere. So let's use this formula. So 1 upon 4 pi epsilon naught multiplied by Q upon R. Okay, potential due to a charged sphere is 1 upon 4 pi epsilon naught multiplied by Q upon R. Alright. So then now we can find out the potential difference between these two plates. Of course, the potential at this plate will be greater than I'm saying plates. Okay, so we can find out the potential difference between these two spheres. Okay, hollow metallic spheres. Of course, the potential at the inner sphere will be greater than potential at outer sphere. But we want to find out the potential difference. So see, potential at inner sphere. Let's call it VA. So this potential will be potential due to the inner sphere plus potential due to outer sphere, right? How much would be potential due to inner sphere? Potential due to inner sphere, potential due to, you can say V due to A plus V due to B. So potential at inner sphere is given by what? It is potential due to this sphere plus potential due to B. Okay. What is potential due to inner sphere? It's 1 upon 4 pi epsilon naught multiplied by Q upon Ra. Potential due to outer sphere on any point which is inside that sphere, it's 1 upon 4 pi epsilon naught multiplied by, I'm taking small r, multiplied by Q upon Rb. But this charge is negative. Okay, this charge is negative. So it will be minus Q upon Rb. Right. Similarly, we can find out potential on the surface of outer sphere. How much will be that? So it is potential due to sphere A plus potential due to sphere B. Okay. So potential on the outer sphere is potential due to this sphere. Okay. Plus potential due to this sphere. So it is 1 upon 4 pi epsilon naught multiplied by Q upon. So potential at any outer point will be what? 1 upon 4 pi epsilon naught multiplied by Q upon the distance of that outer point from the center. Okay. So it is upon RB, right? Plus potential due to B will be what? 1 upon 4 pi epsilon naught multiplied by minus Q divided by RB. Okay. So then if you take VA minus VB, so this term is common, right? Potential due to B is common here and here. So it will get cancelled out. So what remains is 1 upon 4 pi epsilon naught multiplied by Q upon RA minus Q upon RB. right? And then we can take Q also common. So it is VA minus VB is suppose the potential difference. VAB we can call it. So it is Q divided by 4 pi epsilon naught 1 upon RA minus 1 upon RB. Okay. And then we can make denominator same. So it will be RA times RB. Okay. That means we have to multiply this term with RB, this term with RA. So what do we get? We get Q divided by 4 pi epsilon naught. Okay, this will be RB minus RA divided by RA times RB. So this is potential. Okay, or the potential difference between two spheres. And then we want capacitance. So we want charge divided by potential difference. So what is capacitance? Is Q upon V. So if we divide by V, what do we get? So other things will take on other side. So 4 pi epsilon naught RA RB will take on other side. So this is equal to 4 pi epsilon naught RA times RB divided by RB minus RA. So this is the formula for capacitance due to concentric spheres. This is the formula for capacitance due to concentric spheres. Got it? Yes, no? One more type of capacitor which is often used, and it is known as cylindrical capacitor. So let's talk about the cylindrical capacitor. So there is some positive charge on the inner cylinder and some negative charge on the outer cylinder. Okay, so some negative charge will be there on the outer cylinder. So minus Q, suppose, charge on the outer cylinder, right? So now this is Q, this is minus Q. So see, just like we discussed in the case of two spherical, two concentric spheres, see what happens if you take any point, if you consider any point inside, sorry, if you consider, sorry, not any point, if you consider inner sphere and outer sphere, so there will be some potential. We want to find out potential difference, right? So there will be some potential due to inner sphere, there will be some potential due to outer sphere. Okay, and the potential due to outer sphere, which is 1 upon 4 pi epsilon naught minus Q upon RB, it gets cancelled out. Okay, potential due to outer sphere gets cancelled out, right? So similarly, here in this case we have two cylinders. One is inner cylinder, one is outer cylinder. So we want to find out potential difference between these two cylinders. So suppose radius of the inner cylinder is RA. This radius is suppose RA and this radius is RB. Okay, and this is axis of the two cylinders. Okay, so radius of inner cylinder is RA, radius of outer cylinder is RB. So now what will happen if we want to find out the potential difference between cylinder A and B? So there will be some potential on inner cylinder due to inner cylinder itself, and there will be some potential on inner cylinder due to outer cylinder also. Okay, similarly there will be some potential on outer cylinder due to inner cylinder, and there will be some potential due to outer cylinder also. Okay, now it is like this is your closed conductor. So potential due to a closed conductor for all points which are inside the conductor, it will be same. So potential due to B here and here will be equal. Okay, so if you take VA minus VB, then potential due to this one will get cancelled out, right? Potential due to this one will get cancelled out, and what you are left with is potential due to this cylinder only. Got this? I'm sorry. Okay. So then, now how will you find out this potential? So see, we have got this formula for the electric field. We know electric field is equal to minus of dV by dr. Okay. So the cylinder is similar to a charged wire, we can say. Okay. And the electric field due to that charged wire is what? It is lambda, surface charge, the linear charge density divided by 2 pi epsilon naught r. What is r? R is distance of the point from the center. Okay. So E is equal to lambda divided by 2 pi epsilon naught r, and it is equal to minus of dV by dr, right? Then we can find out dV. So therefore dV is equal to, it is equal to minus lambda, lambda divided by 2 pi epsilon naught r times dr. Okay. And we can take its integral. So if we take its integral, dV from B to A will be given by what? It is integral minus lambda upon 2 pi epsilon naught r dr. So here we can take lambda upon 2 pi epsilon naught outside. Okay. So what do we get? So we get it is minus of lambda upon 2 pi epsilon naught dr divided by r. Integral of dr upon r, and from where to where? From B to A, right? RB to RA. Okay. So on left hand side we will get VB minus VA, and it is equal to what? Minus of lambda upon 2 pi epsilon naught. Integral of this thing is equal to log of R. Okay, so log of R, and lower limit is RB, upper limit is RA. Sorry, this is VA minus VB. Okay. Then we can absorb this negative sign inside, or we can say it is log of RA minus log of RB. Okay, this is lambda upon 2 pi epsilon naught log of RA minus log of RB, right? So then if we absorb the negative sign, this negative sign inside, then what will happen? It will become log of RB minus log of RA. Okay, this is the potential difference. Okay, so we saw this in case of a long straight wire. This is similar, right? So actually formula is exact only. Okay, but cases are different. So that was one wire. These are two hollow coaxial cylinders. Okay, this is equal to potential difference between these two cylinders is lambda upon 2 pi epsilon naught multiplied by what? Log of RB upon RA. Okay, and this log is always natural log, right? Unless we write log to the base 10, it is always natural log. Okay, so we got the formula for potential. And what is lambda? So lambda is Q upon L. Okay, lambda is Q upon L. So we get V equals to 1 Q upon 2 pi epsilon naught times L multiplied by log of RB upon RA. And then we can move V on this side, other things on other side, and we can find out the capacitance. So therefore capacitance of a cylindrical conductor, cylindrical capacitor we can say, is given by C is equal to Q upon V, and if we take Q upon V, it implies that we get 2 pi epsilon naught L divided by log of RB upon RA. Okay, so this is the formula for the capacitance of a cylindrical capacitor. Got it? Yes, no?